Section 3.10, temperature. Have you ever thought about what temperature is and why something's hot or cold? I think a lot of us haven't. We just, we understand that things are warm or cold, but we don't think about why. Well, when we talked about the states of matter, about how particles are in constant motion. Even solid particles are moving. So they all have a little bit of kinetic energy because they're moving. Even if they're not traveling a distance, they're moving back and forth. They've got kinetic energy. Well, that kinetic energy is thermal energy also, that movement. So thermal energy is a form of kinetic energy, that constant random motion. Temperature is a measure of that energy. Temperature and heat are not the same, but temperature is a measure of thermal energy. So if something is warmer, it has more thermal energy, the particles are moving faster. So the stupid analogy for this one is think about people walking barefoot on a beach. If you go to Pismo, where it seems like it's always about 60 degrees and windy and cloudy, which, coming from here in August, it's like paradise, right? It's cold there and we're hot here. You can stroll barefoot on the beach. I don't know if that sand ever gets hot, right? It's cool. And so you can walk barefoot and it'd be just very, very comfortable. This analogy works a little better in Reedley. In Reedley, we have a place called Reedley Beach. Sounds all fancy. It's just a real sandy place on the Kinks River. But, if you don't have a pool or air conditioning, you can go and cool off in the really, really cold river. But there's sand there, okay? And imagine, what if we had a big patch of sand out in the parking lot here at COS? Would that get hot? Oh, man. So would people just stroll slowly barefoot through that hot sand? No, we say they'd hot-foot it, right? They're like, okay, because it's hot. Okay, so when a substance is hot, its particles are moving faster like barefoot people on sand. When the substance is cold, they'll move slower. Okay, so temperature is a measure of thermal energy, the random motion of particles. Again, be careful not to confuse temperature with heat. They're different. Heat is energy and is the transfer or exchange of thermal energy from one thing to another, whereas temperature is the measure of that. Heat always flows from the hotter object to the colder object, and we understand that. You take ice cubes and you put them in lukewarm water, and what happens? The lukewarm water is warmer, and it transfers its heat energy to the ice cubes. And the ice cubes warm up and the water cools down, and they'll go to the same temperature eventually. Temperature is, again, something that can be measured. We talked about units of energy. We're going to talk about units of temperature. This slide gives you a lot of details. I'm going to let you read that on your own and just go to this comparison of temperature scales. So there's 3 main temperature scales that are used. The Fahrenheit one is the one we are most familiar with. When they say it's going to be 94 degrees today, they mean 94 degrees Fahrenheit. Okay? On the Fahrenheit scale, water boils at 212 degrees Fahrenheit and it freezes at 32 degrees Fahrenheit. Classic example of English units, right? Just weird numbers. 212 and 32, where those come from, right? Okay, so the Celsius scale is a metric scale of temperature, and it's based on factors of 10. And so they said, well, let's say that 0 is the freezing point of water, and we're going to assign the boiling point of water a temperature of 100 degrees. And they did that because boiling point of water, that is a temperature that's easily achieved without even any technology much. You can have a pot and a fire and water, and you can get 100 degrees Celsius. If you have ice water, it's going to be 0 degrees Celsius. And so those are 2 temperatures that are very easily achieved. So they said those are going to be 0 and 100 degrees. And then they divide it up in between. Well, because this difference is 180, and this difference over here is 100, the temperatures degrees are not the same size, and 0 is not in the same place. And so the relationship between those two temperature scales is more complicated than the relationships between units that we've been talking about so far. We can't use dimensional analysis to solve these. We need an equation. Basically, it comes down to algebra. We need an equation to relate those two. And then there's a third temperature scale, the Kelvin scale. And if we look here, the freezing point of water is 273.15. The boiling point is 373.15. And you might think, well, gosh, those are really strange numbers. Well, yes, they are. But notice that the difference between them is 100 degrees. The Kelvin scale is the Celsius scale with the 0 offset. This Kelvin scale is based on the concept of absolute zero, the temperature at which the motion of all particles ceases. Okay, we actually haven't, as far as I know, have not been able to achieve a temperature of 0 Kelvin. It's minus 273 degrees Celsius. That's really, really incredibly crazy cold. They've gotten pretty close. We will use the Kelvin scale a lot when we talk about gases, and so we need to understand how to convert. The conversion between Fahrenheit and Celsius is an equation. The conversion between Celsius and Kelvin is also an equation. These are the equations. You should memorize these. So Kelvin is Celsius plus 273.15. That one's pretty easy to remember as long as you remember that weird number. And Celsius is Fahrenheit minus 32, that quantity divided by 1.8. If you're using that equation and you're coming up with the wrong answer, make sure you're doing that on your calculator right and either using parentheses in the numerator or pressing equals to make it complete that subtraction, because this is one of those situations where people have issues with their calculators. They understand what they're doing, but they're not communicating with their calculator very well. So let's do a couple of examples. Convert 358 Kelvin to Celsius. So these are, again, straightforward examples. So there's only one number here, right? So let's write that guy down. That must be what we're starting with, 358 Kelvin. And we want to convert that to degrees Celsius. By the way, the Kelvin, it's not a degree Kelvin, it's just a Kelvin. Is there an equation relating those two things? Yes, there is. The equation is that Kelvin equals degrees Celsius plus 273.15. So that's the equation that relates the two of them. But we're given Kelvin, we want to find Celsius, and so we need an equation that says degrees Celsius equals something. I highly encourage you to rearrange your equations first and then plug the numbers in. Because when you do it the other way around, all kinds of bad things happen, resulting in wrong answers. So to rearrange this equation, we need to subtract 273.15 from both sides, and we end up with K minus 273.15. Okay, if you need help with rearranging equations, come talk to me. I just can't take class time to do that. So degrees Celsius, now we put the number in, 358 minus 273.15. And that's going to equal, what does the calculator say? 358 minus 273.15. Calculator says 84.85. Units are degrees Celsius. Because we're using an equation, you don't put the units into the equation, they're not going to work out. Yes?
Since it's only 358, would you have to do that to 3 significant digits, or with temperature?
That's a good question. What about the significant figures? Well, this is subtraction. And so then we're going to look at where's the uncertainty. In that number, it's in the ones place, and on this number, it's in the hundredths place. The ones place is larger uncertainty. And so we're going to round this off to the ones place and call that 85 degrees Celsius. Okay. Another way to think of this is a Kelvin and a degree Celsius are exactly the same size unit. Okay? If we had an uncertainty of plus or minus 1 Kelvin, we should end up with an uncertainty of plus or minus 1 degree Celsius. We're not going to make our number more precise just by changing the units. Okay? Any questions? I'm still learning this program. Okay, here's another guy. Convert 139 Celsius to Fahrenheit. Well, again, we're only given one number. (139 degrees Celsius). We're trying to find degrees Fahrenheit. Do we have an equation that directly relates those?
Yes.
Yes, we do. Okay, so it was degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. Did I do that right? Okay. So again, I'm giving you the hard examples in class. We have to rearrange this equation because we need degrees Fahrenheit equals something. So this equation is a little more complicated to rearrange because it's got fractions in it. And so some of you are a lot better at seeing how to rearrange these than others. Fractions mess people up. Think of this as a fraction also, and then cross multiply. Hopefully you remember that term from math. Cross multiply, get rid of the fractions. If you can see this in your head, you can just ignore what I'm saying right now. So I'm going to end up with 1.8 degrees Celsius equals degrees Fahrenheit minus 32. I got rid of the nasty fraction. My friend who teaches 8th grade math says fraction is the F word. So it just gives her students no end of problems, and you probably remember those days. So now we want to add 32 to both sides, and I'm going to flip the equation over, and we get Fahrenheit equals 1.8 times the degrees Celsius plus 32. So now we can plug our number in there. Number was 139. So 139, let's just be consistent here. 1.8 times 139 plus 32. And my calculator is telling me 282.2. That would be degrees Fahrenheit. And so then again, we're faced with the idea of the significant figures. This one's more complicated. It mixes multiplying and adding. Okay, so we're going to take kind of a shortcut approach. A degree Celsius and a degree Fahrenheit are close to the same size. One is less than twice the other, so they're in the same ballpark. Unlike a kilometer and a meter, where a kilometer is 1,000 times bigger, that's a big difference. So we're just going to go with whatever uncertainty was in the original temperature will be the uncertainty in the converted temperature. So our original temperature had an uncertainty in the ones place. So our converted temperature will also have uncertainty in the ones place, and we'll call this 282 degrees Fahrenheit. If you follow the rules of significant figures, that will usually come out, but occasionally there's a little glitch in the significant figures because they're not perfect. But this is a good rule of thumb to use. Any questions? So you got to know those equations. That's the hard part of this.